Well, here we are again on some review YouTube videos. This time we have Thanksgiving to blame, so I'm put together a few of these videos to cover the two challenge questions from the last two lectures of the course that I think are best representative of the types of questions that you could expect to see on the unit exam, and probably the best practice questions for you to test your own ability, make sure that you can master. So again, before you watch these videos in earnest, I would highly recommend that you first try challenge question number 1 and challenge question number 2 on your own, and then when you think you have the right answer, or when you feel that perhaps you can't come to the right answer yourself, at that point, go ahead and watch this video and see whether you understand it after watching the explanation. So the first challenge question we'll be talking about is this one. Being cranky is controlled by a single gene with 2 alleles, and not being cranky is dominant over being cranky. Well, I can't say that's true from my own personal experience. I always thought of myself as heterozygously cranky, but we'll believe the question and say that cranky is recessive. For a population in Hardy-Weinberg equilibrium, 960 people were determined to be not cranky, and 40 people were cranky. Based on this information, and only this information, calculate the allele frequencies for the dominant and recessive C alleles. Well, the question like this is relatively intimidating when you first look at it, because you're not really given much information. You're given phenotypic information. Out of 1,000 people, 960 are not cranky and 40 are cranky, and you're supposed to go from that phenotypic information all the way down to allele frequencies, and that can be pretty intimidating. But trust me when I tell you that all the information you need in order to get to the correct answer here is available in this question. So let's talk out the genetics and the logic first, and then we'll worry about the math after. So as I consider this phenotypically, I realize that being not cranky is dominant. So those 960 individuals, they can either be homozygous dominant for big C or heterozygous. Both of those genotypes will lead to being not cranky. So that's really not informative. We have too many unknowns there in that question. But the only way that you are cranky, according to this question, is by being homozygous recessive. So those 40 individuals, those 40 out of 1,000, they are homozygous recessive. That's the only genotype that will lead to that. That's going to be our key into this question. Well, first, let's determine that genotypic frequency. That 40 individuals, that set of 40 individuals, is 40 out of a total of 1,000. So shown as a frequency, the frequency of individuals who are homozygous recessive is 0.04. On any calculator, if you take 40 and you divide that by 1,000, the calculator will tell you that that's a 0.04 frequency. The other thing that we need to remember when it comes to Hardy-Weinberg equilibrium is that in any population that is in Hardy-Weinberg equilibrium, and this one is, we're told that in the question, the number or frequency of homozygous dominant individuals is equal to the allele frequency of the dominant allele squared, or p squared. The number of heterozygotes, the frequency of heterozygotes, is equal to 2 times p times q. That's 2 times the allele frequency of the dominant allele times the allele frequency of the recessive allele. Finally, for any population in Hardy-Weinberg equilibrium, the frequency of individuals with a homozygous recessive genotype is equal to q squared, or the frequency of the recessive allele. Now, you'll notice, I hope, that we just calculated the genotypic frequency for individuals who are homozygous recessive. It's 0.04. That's the only genotype, according to this question, that can be cranky. What that means to us is we already know q squared. Q squared, the frequency of individuals with a homozygous recessive genotype, is equal to 0.04. If we want to solve for q, because remember, we're looking to calculate the individual allele frequencies, all we need to do is take the square root of both sides. The square root of q squared is simply q. And the square root of 0.04 is 0.2. If you take 0.04 on any calculator and take its square root, you'll see that it's 0.2. So we just determined the allele frequency for the recessive allele. It's 0.2. The last rule of Hardy-Weinberg equilibrium that we need to finish this problem is that P, the allele frequency of the dominant allele, plus Q, the allele frequency of the recessive allele, which we just determined, always equals 1. So if we know that Q is 0.2, then by the definition of that formula, we also know that P is 0.8, because P plus Q must equal 1. And we have solved this challenge question. We have calculated the allele frequencies for both the dominant and recessive C alleles. I would like to take this challenge question one step further, however, and show you how you might do something that you could be asked to do in the future. It's perfectly reasonable for this question to go one step further and ask you to also calculate the genotypic frequency that's the frequency of a particular genotype for the heterozygotes in this population. Now again, we would consult with what we understand of Hardy-Weinberg equilibria, and we would remember that the genotypic frequency of the heterozygotes is always equal to 2pq for any population that's in Hardy-Weinberg equilibrium. Well, we just solved for q and p. So if we take this equation and say 2 times p, which we've determined to be 0.8, times q, which we've determined to be 0.2, we will get an answer of 0.32. 2 times 0.8 times 0.2 is equal to 0.32. Again, this value is the genotypic frequency for heterozygotes in this population, or said more simply, 32% of this population will be heterozygotes. So that's what we're looking for in terms of this challenge question. If we move on to the next challenge question, we see the same exact logic being applied, but we're applying that logic in slightly different ways. We're answering this question in a slightly different manner. We use the same math and the same principles, the same understanding, but how we think about the question will be just a little bit different. This question states that a newspaper story on AIDS reports that an allele, dominant R, confers complete resistance to HIV when you are homozygous for that dominant allele, and that 1% of the human population is indeed homozygous dominant R and resistant to HIV. The story also states that 20% of the population carries one copy of the resistance allele. In other words, 20% of the population is heterozygous. When writing this newspaper story, did the newspaper make an absolute guess? Did they just pull 20% out of their rear ends? Is it an approximation? Or is it an exact frequency, and exactly 20% of the human population is heterozygous for this R allele? And the question tells you to assume that the population being discussed is in Hardy-Weinberg equilibrium. Again, we're going to go to our initial Hardy-Weinberg equations, and remember that the genotypic frequency for being homozygous dominant, that is, the genotypic frequency in this question for being homozygous dominant R, is equal to p squared, if the population is in Hardy-Weinberg equilibrium. The genotypic frequency of being heterozygotic is equal to 2 times p times q, and the frequency of being homozygous recessive is q squared. That will always be true for any population that is known to be in Hardy-Weinberg equilibrium. Now let's think of the information that this story gives us. What this story tells us is that 1% of the human population is homozygous dominant. In other words, this question is telling us that p squared, that is, the genotypic frequency of homozygous dominance, is equal to 1%. Well, 1% really doesn't help us because that's not a frequency. We need to remember that from a frequency perspective, 1% is equal to 0.01. So now we know that p squared is equal to 0.01. We would like to solve for p. In order to solve for p, we should take the square root of both sides of this equation. When we take the square root of p squared, we're left with just p. The square root of 0.01 is equal to 0.1. So in this question, the allelic frequency for the dominant allele is 0.1. If you remember from the previous question, p plus q must always equal 1 for any population that is in Hardy-Weinberg equilibrium. And so if p is equal to 0.1, q must by definition be equal to 0.9. The two allele frequencies, when added together, must equal 1. We go back to the question. The story also states that 20% of the population carries one copy of the resistance allele, or in other words, is heterozygous. The newspaper story is reporting that the genotypic frequency for heterozygotes is 20%. We're asked to check that. To do that, we need to remember that genotypic frequency is equal to 2 times p, 0.1, times q, 0.9. When we do that calculation, we see that 2 times 0.1 times 0.9 is equal to 0.18. The genotypic frequency of heterozygotes in this population as described is 0.18, or 18%. When we go back to the question, we see that the newspaper reported this frequency as 20%. Well, it doesn't seem to me as though they guessed that number, but certainly it's not the exact frequency. So we would end by saying the newspaper rounded. They approximated. They took the 18% exact frequency and they rounded up to 20%. And that's the answer to this question. The remaining two questions go in a little bit of a different direction. They're a little bit more mathematical, but to be fair to those questions, they're also a little bit less population genetic-y. The two questions at best capture Hardy-Weinberg equilibrium math, and the way that I expect you to know Hardy-Weinberg equilibria are these first two questions. They're the challenge questions here, which is why I'm reviewing them. I hope these questions make sense, but of course, if they don't, please feel free to contact me or come to office hours, and I'd be happy to go over these in a little bit more detail with you.